Okay. Good morning, students. Today's lecture will in the today's lecture we'll move on from what we had done last time around. So quickly let's revise what we had done last time around. In the last two lectures, we have seen what is an optical fiber communication in the sense what is how the OFC system has developed over a period of years. That is basically the historical development. So somewhere around 1960s, people started envisioning the use of fiber for communication, but it was not very efficient in those days. It was somewhere around 1980s that the fiber system really picked up, and from then on, the systems have been in use. In the last lecture, we discussed regarding the generations of the optical communication. So we have five generations till now, and each generation just exceeds the expectation from the previous generation. So in the first generation, you had let's say about 100 Mbps of data rate, but in the second generation, that increased to about 150 Mbps. In the third generation, it was about 10 Gbps and so on. So currently, we are at the fifth generation where we get close to about 20 Tbps. The wavelength of operation is somewhere in the 1500 nanometer range. I explained to you that since the frequency in OSC is very, very high, we often deal with only the wavelength. And since wavelength and frequency are inversely related, the wavelength becomes a very small number, usually in nanometers for this particular course. So the wavelength of operation for the OFC system in the fifth generation is in the range of 1500 to 1600 nanometers. The center wavelength is 1550 nanometer. You need to really understand this. This will be used again and again in this particular course. Then we have seen the electromagnetic spectrum and where exactly the OFC system lies. So OFC system lies somewhere between 1.7 to zero point 0.8 micrometer, and it is near the infrared region, close to also the visible spectrum. So we had drawn the electromagnetic spectrum starting from millimeter wave all the way till cosmic rays. We have also seen in the last lecture the three operating windows of the OFC. So I had particularly asked you to keep in mind that the generations is a separate issue and optical windows are a separate issue. By generations, we mean what is the expectation of the customers in the sense of from an OFC, whereas the optical window is basically the three windows on which the optical fiber is going to operate. So when it comes to the windows, we have three windows. So very quickly, we have the first window, which has a center wavelength of about 850 nanometer. We have a second window, which has a center wavelength of about 1310 nanometer. In few books, this could also be stated as 1300. Then we have the third window. This is where we operate these days, and this operates in 1550 nanometer, right? And this range is somewhere between 1500 to 1600 nanometer, but the center wavelength is 1550 nanometer. The components which are used in this third window, so we use laser as the source. We use APD, avalanche photodiode, as the receiver. We use EDFA, that is erbium doped fiber amplifier, as the amplifier. And we still have to do these components, which we'll be doing in particular modules. And as the fiber, we use what is known as the single mode fiber, or SMF. There are two types of fibers, uh, multi-mode fiber and single mode fiber. We use the single mode fiber in the third window. I had also specified the difference between the two. We'll be doing that in the today's lecture as well. Right? So a multi-mode fiber is used for short distance, like an office environment, whereas a single mode fiber is used for long distance, let's say 3000, 5000 kilometers or so. Then lastly, in the previous lecture, we did the general system for an OFC, and we saw how it is different from an electrical system. There are two differences. In the source side, uh, before the modulator, we need a source which will convert electrical signal, that is flow of electrons, into corresponding light, which is photons. So as the source for the system, if this is the source, Then as a source, I need a device which will convert these electrons into corresponding photons. And likewise, on the opposite end, that is the receiver. So if I have the receiver here, then this should be able to convert light, that is photons, into corresponding electrons, right? So as the source, you could use an LED or a laser. As the receiver, you could use a pin diode or a avalanche photodiode. And these things will be doing in module 3. Okay? I also mentioned to you that transmission is a very simple process because we know what data we want to transmit. However, it is the receiver which is problematic because of the addition of noise, which makes everything random at the receiver. Right? So our receiver structure has to be a very good design so that it becomes easy for us to receive, and less and less errors are also occurring. So just to give you a glimpse of what a receiver structure would look like, we'll be doing this in module 3 also. So let me draw this particular receiver. So this is an OFC receiver, that is let's say more specifically a digital optical fiber cable system receiver. Right? I have specified here digital OFC receiver, but you should know by default that OFC system is digital imaging, right? So the signal which is incoming at the transmitter, we assume that it is already sampled, quantized, and encoded to make it a digital signal, right? Okay, so we are doing the receiver here. So as the first block, we have an encoder, and this will be the source. This will be the digital source or digital information, if you want to call it. This will be the digital information. Then we have the laser. So I'm assuming here that the source is the laser. So laser basically is a diode. So from here we'll get light out. So let me call this HF. Then we'll have an optical fiber cable. I'm drawing it this way, but there's a specific way of drawing the OFC, and that we'll see today. So this part would be the source, and let me draw the receiver. Let me draw the receiver at this end. So at the receiver, it will be the opposite process. So we'll have these photons coming in, and this will be your pin diode or an APD. It's again a diode, so that's why I've drawn it in the form of a diode. And from here, it goes to an amplifier and an equalizer. We still need to see what this equalizer will do. Basically a filter. And then from here, it goes to a decoder. And from here, you get your output. Okay. So the bottom part would be the receiver. So this entire diagram shows you the block diagram of a digital optical fiber link. The input signal from information source, this will be encoded into for the optical transmission. The laser circuit or drive circuit or diode circuit is going to modulate the signal and then encode it, and this will be sent through the fiber. Uh, this this fiber is then going this signal from the fiber is then going to be received by the pin diode or the APD, whichever we are going to use as per application. So this will be detected by those receivers, and this will be followed by an amplifier. If I want to be more specific regarding this amplifier will be a front end amplifier. So we'll be using a front end amplifier. Okay. I don't know if you're aware of the different types of amplifiers. No need to worry about that now. But we'll be dealing with the types of amplifiers uh, a little later, right? Probably in module 4 or module 5. Okay. So this will be a front end amplifier, and then this will be followed by an equalizer that is basically a filter. This is a very important concept, and this will provide gain as well as linearity to the signal, and it will reduce the bandwidth over which the noise can operate on your data signal. Right? So this is a general structure of an optical fiber receiver, the complete receiver. Okay. So right now this is just a glimpse of it, but we'll be doing the details. In detail, what is this amplifier? What is this equalizer? Okay. So having done that, now let's move to uh, what an optical fiber looks like. So I want to do what is the structure of an optical fiber. Structure of an OFC, that is the optical fiber cable. Okay. We have already done the advantages and the disadvantages. So advantages are in terms of bandwidth and less uh, electromagnetic interference. Disadvantages, you could state that initial cost is high and so on and so forth. I've given you the advantages and disadvantages. Applications, there are many applications. So you could use them as uh, at the backbone. So mostly your backbone uh, network is always OSC because it provides very high, very large bandwidth. The front end could be, let's say, a wireless network. So what happens in our campus is basically the same. So you have an optical fiber cable that comes to the gate of the college, and then inside you have Wi-Fi. Right? So it is mostly like a radio over fiber case. Entire bandwidth which is provided to the campus is through the OFC, but it gets distributed within the campus based on different Wi-Fi slots or different Wi-Fi hubs. You could also use them for sensors. IoTs use fibers a lot. You can also use them for military applications and many other applications. Okay? So let's now look at the structure of an optical fiber. So from the side, the optical fiber looks like this. So you have a structure from the side which looks like this, and you have the inner structure having a refractive index as N1 and the outer structure having a refractive index N2. I'll define what is the refractive index in a minute. The outside structure here is known as the cladding. The inside structure here is known as the core. Let me also draw an outside structure that comes in with this fiber, and I'll do that in a dot. So these dotted lines, these are just to protect the fiber. These are just to protect the fiber, and this is known as a buffer. Okay. So the most important part inside an optical fiber is the core, and it is inside the core that the light will propagate. Uh, Sometimes in some books you'll also read this buffer as a jacket. Okay. So this just provides protection to the fiber. So let's see what is this refractive index very quickly. The refractive index N is defined as C by V, where C is uh, velocity of light in vacuum or speed of light in vacuum, and V is the speed of light in a medium. So this medium could be glass, could be sand, could be air. So different mediums are there, and in the numericals you'll see that these mediums will be provided to us. So if we take air for instance, N will be equal to 1. This is for air. If we take water, N will be somewhere around 1.33. This is for water. If we take glass, then N will be around 1.5. Okay. You don't have to memorize these values. These would be given in the numerical. If nothing is given in the numerical, we just assume that the medium is air. Okay, so what will be the velocity in the air? So those will be the values for the refractive index. Okay? So what is the use of this cladding? Basically, as I told you, the core is light is only going to propagate in the core. So the question arises, why is this cladding required? Though it is not going to help in light propagation, uh, cladding is required because of the following reasons. It's going to add some strength to the fiber. It is also going to protect the core from any external environment, external issues, and it is going to restrict the light from escaping the core. Right? Same is also the job to be done by the buffer, but we hope that the light never escapes the core and the cladding and goes into the buffer. Right? So the light must always remain in the core, and we'll see why that is the case. That is what is known as total internal reflection. Right? However, the cladding is required because it will provide the strength and it will ensure that the core uh, stays safe from the outside world. Okay. So this is the structure. If you want to see, you can also view from a front end how the fiber would look like. So from the front end, this would be the core, this would be the cladding, and then you would have a buffer. Right? So this will be a core. So I'm just going to write N1. This would be the cladding. This would be N2. So the fiber would look like this from the front end. Okay, and then you have the jacket there outside, and so it looks like that. Okay, so there are different types of optical fibers that we can define before we can see how the how the light is going to propagate inside the fiber. What your book basically does, or what mostly the notes do, is that they specify how the light is, what are the types of fibers based on different aspects. Then they also talk about, based on refractive index and those kind of things. And students usually are not in a position to understand that. So what I do first is I explain that how light will propagate inside a fiber. Once that is understood, then we are in a position to understand what are the types of fibers, because the types of fibers will be based on how the light is going to propagate inside the fiber. Okay? So there are different ways of understanding this operation, but over a period of time, this is what I've done, and it works for the student. So I'll be following the same. So we'll first understand, or try to understand, how light is going to propagate inside an optical fiber. Right? So these are known as this is known as the ray theory. So the ray is nothing but the signal that you are going to try to propagate inside the fiber. Okay? So let us look at the diagram and let's see how light is going to propagate inside a fiber. Right? So let us assume that uh, there are two materials which exist. The reason why we are taking two materials is because if you see, the fiber has two materials. One is this core here, and the other is the cladding. So if we are able to understand how light propagates with respect to two materials, then we can apply the same theory inside an optical fiber. Right? So let this be the boundary, that is the boundary between two materials. This is material 1 here on top and material 2 at the bottom. Let the material at the bottom, let the material at the bottom have a refractive index N1, and let the material on top have a refractive index N2, which is less than N1, which is less than N1. So please remember, this is applicable for henceforth, that the refractive index of the cladding N2 is always less than N1, If you flip this, that is, if you make n2 greater than n1, then our entire derivation does not apply. Right? So we are starting under the assumption that the material n1, the material having refractive index n1, and there's another material having refractive index n2, which is less than n1. So this is what the derivation is done under that assumption. Okay. Now let this be a normal line, a perpendicular line. Now let us give it let us give this material some incident light. Let me redraw this again. Let us give this material an incident light, that is light which is going to be incident at this boundary. Let this incident light make an angle of phi 1 with the normal, and let it make an angle of some theta 1 with the horizontal. Now two things can happen to this particular light. Because the materials have different refractive index, therefore the velocity of light inside both these materials is going to be different. And if you see, n here is c by v, therefore higher n, that is higher value of refractive index, is going to give lesser velocity to the light, right? And a lower value of the refractive index will give a higher velocity to the light, right? So now when this light enters n2, since n2 has a lesser refractive index than n1, I repeat again, once light enters into a material with refractive index n2, since n2 is assumed to have a refractive index less than n1, the velocity of light inside material n2 is going to be larger or higher, right? So what is going to happen to this incident light? Two things are going to happen. One, it is either going to refract, and part of it is going to reflect. So this is the refracted ray, if you want to call it, or refracted light, and this is going to be the reflected light. Okay, what about the angles here? Let this angle become theta 2, and since this is phi 1, let this angle be some phi 2, right? So this is what is going to happen when you take two materials with different refractive indices, right? So the angle, just to define, the angle of rays are measured with respect to normal. This is the line which is drawn at right angle to the boundary between two materials or two refractive indices. The angle that is incoming, that is this particular angle theta 1, this particular angle theta 1 or phi 1, that is known as the angle of incidence, right? This is known as the angle of incidence, and the outgoing ray, this is known as the angle of refraction, right? So you have angle of incidence phi 1, and then you have angle of refraction, that is going to be phi 2, right? So this is how it is happening in general, right? However, this diagram or this situation is not a good situation in the case of optical fiber, because if you view this as N1 being the core and N2 being the cladding, you can see from this diagram that once light once light enters a different material, that is the cladding, from here on, you can see that some light is refracted. That means it is moving or propagating only inside the cladding. However, we do not want that. What we want in this diagram of the optical fiber is that we want the light only to remain inside the core of the fiber. We do not want the light to go anywhere outside. we want the light only to remain here. We do not want any light to go to the cladding. That's not a good situation because light is escaping the core. So I want this light to be always inside the cladding. So if I compare this diagram with the diagram below here, I want all the light to remain only inside the core. That means I want all the light to remain only here. I do not want any light to go here, right? That's not a good situation for us, right? Therefore, there has to be some mechanism through which we ensure that this incident light, when it hits this boundary here, it only gets reflected. It does not get reflected, right? So this is something that you will have to visualize, right? So how can that be done? This can be done by visualizing this. If I am able to hold this line here, just assume that you are able to hold this line, right? It is like a stick which you are holding. And if I now start pulling this line towards the horizontal this way, right? So what is going to happen once I pull this line towards the horizontal? This line here, which is the refracted ray, starts moving down here, right? You can see that once I move this, that particular line, refracted ray, starts moving down here. So there is going to be some angle, right? Probably, let's say the line looks like this. When I move this stick here, it could happen that this particular refracted ray just lies on the horizontal, right? Then if I further move this line a little towards the horizontal, and let's say this line comes to this part, it will happen that this refracted ray, which is on the horizontal, now only gets reflected, right? So the job that I have to do is to ensure that this incident angle is at such an angle, or this incident light or ray is at such an angle that there is no refraction that takes place. There is only reflection which takes place, right? And if that happens, we call that as total internal reflection, TIR, right? And it is under this condition that an optical fiber is going to operate or work, right? So let us draw these diagrams and see if we can really understand. Let me draw these diagrams, 3 diagrams, and then I will ask you whether you have understood or not. Okay. So let me draw the first diagram. So the first diagram is basically the one which I had just drawn. So let me just redraw that quickly. So the first diagram is going to have a horizontal, then you're going to have the normal. You have an incident ray. Let this make an angle theta1. You have n1 here. You have n2 less than n1 here. You have a refracted. You have a refracted ray and you have a reflected. This is a reflected ray. That is a refracted ray. This is the incident ray. This is theta1. This is obviously theta1. This is theta2. And let us call this angle some phi2, and this is some phi. So like I explained, if we keep pulling this incident ray, if we keep pulling this incident ray this side, then what is going to happen? There is going to be a particular angle. There is going to be a particular angle where there will be a particular angle where the refracted ray, ray is just going to become a reflected ray. So let's look at that diagram. So the case here. Now let's say the incident ray has come somewhere here. And This is the incident ray. It is at an angle that such that the refracted ray lies just here. The refracted ray lies on the horizontal, and then you also have the reflected. Okay, so here what is going to happen? The angle phi 2, if you see from the diagram on top, is just going to be a 90-degree angle. So you have phi 2 equal to 90 degrees. This angle of theta 1 will now be called as the critical angle theta c, and this angle of phi 1 will be called as phi c, again the critical angle. Right? So in this diagram, let me now name this diagram. This is diagram A, which we do not require, but this is what happens in general. This is diagram B, where we have increased the angle for the incident ray, and because of which the refracted ray lies exactly on the horizontal, and then the part of the light is also reflected. This is also a diagram which we do not require, because if you now visualize this scenario in terms of an optical fiber, this implies if I draw the uh, core and the cladding here. Let me draw the core and cladding with a different color. If I draw the core and the cladding, let's say this is the core, and let's say this is the cladding. Diagram B basically implies that some part of the light is at the boundary of the core and cladding, that is here, right? However, we want light only to be inside the core, not even at the boundary. We do not want this brown color. We want only this pink color. We want all the light to be only inside the core of the fiber, right? Therefore, there's got to be a diagram C. There's got to be a diagram C where if, if we look at this diagram B, we need to exceed the critical angle. That means the angle at which the incident ray hits the boundary of the core and cladding has to be larger than the critical angle, right? So in that case, in such a case, if we redraw this diagram and name this diagram C, in such a case, this is what is going to happen. So if you the incident angle would be phi 1 greater than phi c. This will be the incident ray, and there will be no refraction. All of this light is just going to be reflected, right? And this scenario in diagram C is known as total internal reflection, because internally itself you get everything, all the light reflected inside. So you do not have no refracted ray. There's no refracted ray, right? So this is the scenario which we basically require, right? So now let me go back and ask you, anyone, do you have any questions on this? It's a very important concept. Your entire optical fiber communication is dependent on this. Any questions? Anything which you have not understood? Anybody? So the basic idea here is that when the light ray is going to encounter a boundary, of two different materials or medium, so part of this signal or the ray, this is going to be reflected back, part is going to be refracted, right? But we do not want that scenario. We want all of this light to be reflected back into the same medium, that is the core. So any questions on this? Anybody? Okay. So let us go ahead. So now if we look at the diagram 1, let's see, write this in a bracket here. If we look at diagram 1, we can apply the very popular Snell's law in that diagram. And according to the Snell's law, you'll have N1 sine phi 1 equal to N2 sine phi 2. Okay, so N1 less than N2, it's just going to bend towards the normal. But if you have N1 greater than N2, it is going to bend away from the normal. Right? So that is what I explained you with in regard to the refractive index. What is our assumption in terms of core and the cladding? So for us, the cladding refractive index will be less than that of the core. Okay. So this is the very popular Snell's law. So you have N1 sine phi 1 equal to N2 sine phi 2. So let us do that mathematics here. So I'll rewrite the Snell's law here. So according to the Snell's law, based on that diagram, you have N1 sine phi 1 as N2 sine phi 2. Now if you look at the critical angle, now if I go back to the diagram and if you look at diagram C, the angle of incidence at which the angle of refraction becomes 90 degrees. So in diagram B, so there is an angle of incidence at which the angle of refraction phi 2 is becoming 90 degrees. That is known as the critical angle. That is known as the critical angle. So in this case, in diagram B, we are going to have phi 1 equal to phi c and phi 2 equal to 90 degrees. Right? This is what we obtained from diagram B. So let me scroll down and write that here. So as a next equation, we have phi 1 equal to phi c. We are calling it as the critical angle, and phi 2 is 90 degrees. Right? Now let's substitute this phi 1 equal to phi c and phi 2 equal to 90 degree in the Snell's law. So what we'll have is, in that case, N1 sine, instead of phi 1, I'll substitute phi c. And when phi 1 is phi c, phi 2 is 90 degree. Therefore, RHS becomes N2 sine 90 degree. Right? We know sine 90 is 1. Therefore, if I cross multiply, sine phi c will become N2 by N1. If I take this N1 on this side, and sine 90 is 1. Right? Or phi c is just sine inverse N2 by N1. So this is your critical angle. This is your critical angle, which is sine inverse N2 by N1. So you can see here that the critical angle is dependent only on the refractive index of the core and the cladding. That's all. It's not dependent on anything else. So if we can have the refractive index of the core and cladding in a particular fashion, we can ensure that phi c is the angle is such that phi c can be met, the critical angle can be met, and therefore the light will always be inside the core. So this kind of a design we'll see in later modules, and we will see what exactly N1 and N2 values could be and how we can achieve this phi c. Right? So what is this total internal reflection? So if you scroll down here, the total internal reflection, how do we define this? Right? So if the angle of incidence is greater than, right, if your angle of incidence, so this angle phi c is greater than, if the angle of incidence phi 1 is greater than the critical angle phi c, then we say that total internal reflection occurs because the light remains only in the denser medium, that is because N1 is greater than N2, so N1 becomes the material having N1 becomes the denser medium. So in this case, the light will be reflected inside the medium, inside the denser medium, inside the denser medium. In this case, there is no refraction. There is no refraction, right? So this is known as the total internal reflection, and this diagram here basically shows us total internal reflection. So when phi 1 is greater than phi c, you only have reflection inside the denser medium. You do not have any kind of refraction that occurs, right? So now next also discuss another important criteria, which is known as the acceptance. The acceptance or the acceptance angle will do its mathematical relation and value as we move on with this module. But basically what this says is that the acceptance, the light or the incident angle should always be such that there is only total internal reflection which happens inside the core of the file. Okay. There is also a mathematical equation for this, and that we'll be doing as we move on, as I just told you, right? So this is just to give you an idea. Uh, this is the acceptance angle of the fiber to ensure total internal reflection, right? And we'll see very soon, probably in the next lecture, that this acceptance, this entire thing becomes conical in nature. It is called as an acceptance cone. It is conical in nature, and we'll see exactly how it looks like. Okay. The next important aspect is known as numerical aperture, in short NA. From an exam point of view, you will always have a problem based on NA. They'll ask you to find the value of NA. This is a term which has been taken from the theory of lenses. Lens, okay, concave and convex lens. It basically implies the light gathering capacity of a fiber. So how much light can this fiber gather is known through the numerical aperture. I'll just give you the formula now. We still have to derive it, and once we do that, you'll see exactly how it is. The formula basically is, you don't have to remember this. Once we derive it, you'll understand. The formula is Na is N2 square minus N1 square, which is some sine theta A, right? So this, again, I state you don't have to remember this formula. We'll derive this probably in tomorrow's lecture, right? So here N2 and N1 are the refractive indices of the cladding and the core, and theta A here is the acceptance angle which we will be deriving through this acceptance cone, which I stated earlier. Okay? So this light gathering capacity, or figure of merit if you want to call it, is obtained through the numerical aperture. Okay? Again, a mathematical value which we will be deriving very soon is known as the acceptance angle, which I had stated earlier. And this acceptance angle can be found as this. Theta A is sine inverse Na, which is also sine inverse root of N2 square minus N1 square. And that you can see from this particular equation. All I have to do is just sine inverse. So sine inverse Na or sine inverse N2 square minus N1 square. So this is the acceptance angle. So there will be numericals based on that. The only thing is we have to see how we can derive these equations. So we don't have enough time to derive these equations. This we'll be doing in the lecture tomorrow. So we'll start with the mathematical aspect. I think we have already started with the mathematical aspect, but we'll see how we can derive these two equations, and then we'll try to solve problems based on this. The numericals are very simple if you understand what is given to us and if you understand what we have to find out. Okay. And once we do this, the derivation and the numericals based on this, we will be in a good position to understand the types of fibers, and that is exactly what we want to do. So we are also going to see after the derivation what is the classification of the optical fiber. So we have already classified them as single mode and multi-mode, but we want to understand this concept of mode, and we want to see what is the single and multiple. We can also classify the fibers in the form in relation to refractive indices. It is known as step index and graded index fiber. So we can also do that, and we'll see understand that how we can do that. There are diagrams based on that to understand, and then we'll see how which are the fibers which are most commonly used, like single mode, are they step indexed and so on. What are the mathematical relations there? What is this idea of mode? What is this mode? Why are we calling it single mode? Okay, so this idea of mode is also something which we want to check. So this is all. This is everything that we are going to do probably in tomorrow's lecture. So we'll start with the mathematical aspects. So I suggest you do not miss the lectures. Otherwise, it will become a little difficult to understand through the book. Okay. Apart from this mathematics, rest of the part is theoretical with some more mathematics on it. So it will be easy for us to complete this module very soon. Okay. So you will definitely have this module in your IA1. Okay. And the mathematics is something for which you'll need help. Okay. So please attend the lectures. So I think it is already time. So I'll see you in tomorrow's lecture. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Welcome. Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.
Thank you, sir.
Welcome. Welcome.